Okay. Well, first of all, I want to thank the organizers for inviting me. When I, oops, I'm already on, here's my title. Okay. When I was given this topic, I quickly learned there was far more information than I could address in a short period of time. So the best I can do is at least touch on several of the techniques that have been used from an orbital perspective to address volatiles on the moon. But as you can see from what my summary message is, I'll pretty much end it very much the same way Larry did, namely that we certainly know a lot more now than when we did even just a decade ago. However, there's a heck of a lot more that needs to be done from orbit in order to really understand the character and nature of these volatiles. So with that sort of broad introduction, let me walk through some of the techniques. And what I've listed here are the various approaches, more or less in order of detection of volatile species or characteristics. And I'll walk through them not necessarily in the same order here, but I'll touch on each of them to remind you what it was that was found and what sets the stage for much of the rest of the discussions of this workshop. And I think most of you should be familiar with these: the neutron spectrometer, the basic imaging, the near-infrared spectrometer, the L-cross experiment, which was active, and actually I won't have time to touch on. I'm assuming Tony will, well, actually the rest of this particular session will focus on L-cross, but then also mention the radar and the UV spectrometer and the most recent one from the LOLA altimeter. Now, of course, that's also very important to mention the related measurements, although they don't directly identify water or volatile species. They really are very important for understanding the environment and the stage. Clearly, the temperature of the surface is very important, and I'll just allude to that in the discussion here. But it's one of the essential environmental conditions that allow or don't allow volatile species to exist currently on the moon. The permanently shadowed areas, of course, is not a direct detection, but it's very important in an environmental area. The last two topics here, unfortunately, I simply will not have time to talk about, but I feel they're very important relative to the volatile issues, namely that the energetic particles from principally the solar wind are extremely important for some of the conditions and production of some of the OH that were seen on the surface. And of course, the magnetic fields are important because they may, in fact, shield parts of the surface from these energetic particles. So these last two components are all related to the topic I've been given, namely what can be measured from orbit, and all of these are characteristics that are directly relevant to volatile species and can and have been measured in different degrees of completeness from lunar orbit. With that sort of general introduction, let's go ahead and jump right in to the first hypothesis that really started a lot of the enthusiasm about thinking seriously about volatiles on the moon, namely the recognition from the neutron spectrometer on Lunar Prospector. This is now 15 years ago, how quickly that fades. But only 15 years that we've really recognized that at the polar areas there's a concentration of hydrogen. This measurement was very clear that using the neutron spectrometer on Lunar Prospector, both poles detected a hydrogen-bearing species somewhere in the upper parts of the regolith. And that started a whole host of discussions and the subsequent instruments that we now benefit from having information on. So following up on the Lunar Prospector, of course, LRO flew a more modern neutron spectrometer, the LEND instrument, and this is a a paper that compared the LP, the Lunar Prospector data with the LEND data, translated more or less to the same kind of resolution. And to a first order, they're agreed, which is good. But of course, LEND allows a higher spatial resolution with the collimation that the detector has. There's other issues that, or other differences that the LEND instruments provides. But it provides us a whole new look at, again, both poles, and has identified at higher resolution some very interesting topics, which we were hoping would resolve the issue, but as a good science experiment, it simply raises a lot more really interesting topics. What I show here is comparing these I should have mentioned are all data from the south pole of the moon, which are probably familiar to most of you. And shown here are the LEND measurements on the left, and on the right are some of the imaging analyses, principally by Ben Bussey and his group, analyzing where you have solar illumination, where you might have earth shine, and where the permanently shadowed areas occur. So the top one on the right is where there are shadows, and in particular the yellow and red are the most important, where you have no sunlight. The one on the bottom right is his analyses of where the maximum solar illumination occurs, for those of you who are interested in maximizing the time for sunlight on solar panels. And of course those are opposites of each other, but what you notice right away is that the distribution of the hydrogen as detected from the neutron spectrometers isn't exactly coincident with what we see for the permanently shadowed. And there's a whole host of issues that is a very active area of research, and I'm sure we'll hear aspects of that during the conference. So this was a puzzle. This was not expected. We expected to see nice deposits of hydrogen where we have permanently shadowed, but it's not simple, we've learned. Okay, well, let's look a little more closely at Shackleton, the small crater that's almost right at the South Pole, which is a beautifully permanently shadowed area in all of the illumination analyses. And here's a really lovely experiment that was one of the early experiments that came out of the Kaguya mission. Here we have Shackleton, and the X marks where the South Pole is, so it's really right on the South Pole, and the arrow points the direction towards the Earth. And what Hariyama was able to eke out of the terrain camera imaging was look into the shadow and pick up the scattered light from that little rim of illuminated solar radiation, and look into the interior of Shackleton crater. And first thing we see, there's no ice skating rinks. It looks pretty much like a nice bowl-shaped crater. The floor is a little darker than the rim. The walls are steep-sided. But there was no obvious deposits that we were hoping to see. So that was interesting and exciting, but a little disappointment if you're looking for water. Moving on, now leaping 4 years ahead, as Lola began to obtain data for the poles, here's a beautiful image of the detailed topography that comes out of the Lola measurements. And you may notice that the two images are slightly rotated, maybe 10 degrees relative to each other. But essentially, it's the same thing. It really is a beautiful confirmation using two different techniques of the interior of Shackleton. And what Lola was also able to obtain with the measurement of the reflected radiation is a albedo measurement, and it's essentially similar to what was seen in the terrain camera, namely the floor is darker than the walls, and the walls are relatively bright. But no ice skating rinks. even though it's one of the most beautifully permanently shadowed areas. Okay, moving ahead. Oh, and I should point out that the last LPSC, Hariyama gave a really lovely presentation where they looked closely at the multiband imager for that little bit of Shackleton that's exposed, and it's quite consistent with what we call pure anorthosite, which is one of the brightest minerals you have on the surface of the moon. So it's expected that Shackleton really is heavily anorthositic, as you may expect from its location. But that also contributes to the brightness. Okay, well, of course, if you Google Shackleton or ice or the South Pole, this is what you get. So I thought I had to include this image. But let's now segue into some of the spectroscopy discussion. First of all, the UV spectrometer. This is, again, some of the Lyman alpha maps that they've been able to put together from the Lyman alpha measurement. And again, I compare it with both the lens and the optical shadowing measurements, so you can sort of see where you are. And from the paper that was recently published, most of the variations you see, the team believes are textural. What LAMP is looking for is really the spectroscopic character, and this is tricky to get because you're really beating photon by photon measurements. But what they're looking for is shown here and summarized in a nice paper by Hendricks. They're looking for this water primary absorption in the ultraviolet. And what's shown below there is models for LAMP that you would expect to see with 0.5% and 1% water frost. So there's small variations, and that's what the team is actively looking at. And there's a paper that will be presented midway through the discussion on some of the global measurements of this particular analyses. Okay, here's my one slide on Diviner, again to remind us that all of these, whether they're the poles or lower latitudes, are set into an environment on the moon that is really extreme. This was one of the early Diviner papers, but it's one that I particularly love because shown in the same figure is the day and the night global moon on the same scale, namely from 40 to 400 Kelvin. And you really get a sense of the kinds of temperature extremes that each part of the lunar surface encounters during the day and as you transition day to night, and the whole range of temperatures, as well as the polar areas, which has the most extreme of them all. And this will be important as we address some of the time variation issues that are important for some of the spectroscopic measurements that will be presented sort of midway through this workshop. Okay, segueing on to the other spectrometer, of course, I have to talk about the M-cube results. Up in the upper right is the image most people are familiar with from the science paper. In center stage is Roger Clark's more recent rendition of this, where he's been able to eke out a little bit further some of the distribution of the materials. But for those of you who aren't spectroscopists, I do need to remind you what we're looking at here. And I've got this nice figure which is really from the Mars community, because there's water, frost, and ice all over Mars. And what this particular figure shows is the kind of absorptions you see at 3 microns, or between 2.8 and 3 microns, when you have a variety of OH and H2O features. You also have overtones at shorter wavelengths, which of course we don't see on the moon, but there's a fundamental absorption between 2.8 and 3 microns, which is what's being detected by M-cube. Shown on the lower right is a recent analysis that that Shuai Li and Ralph Millikan have been working on to really beat down the thermal component and look in more detail at the distribution of water across the surface. And Shuai Li will be giving a talk halfway through this conference on some of the time variations of this. But this work is ongoing and is a very active area of research. Let me highlight two other aspects just because I think they're really cool. And this is targeted areas that some people are looking at. There was a lovely paper by Rachel Klema at the last LPSC in which I believe she submitted for publication, focusing on one crater, Volatiles, which is a modest thorium anomaly on the moon. And what she's pointed out, and now that you can look at the spectra, that only the central peaks exhibit the OH-H2O absorption. The walls and the surrounding soil have no absorption at all. It's this deep-seated material, which is part of the thorium anomaly, that exhibits a component of OH or H2O materials. Perhaps this is...
Carle, 4 minutes
Yep.
left and 2 minutes to question.
Okay, I'll speed up. Okay, moving on, another one that I love is work by Noah Petro on the Compton Belkovitch, which is one of the beacons of thorium anomalies on the far side. And even if you're not a spectroscopist, you can see those beautiful water bands there. They're really gorgeous. Okay, moving further, it goes, I have to say this, that there's a whole suite of issues that have not been resolved. Some having to do with science, some having to do with exploration, the origin, composition, the time dependence, the type of OH, the compositional affinities, what kind of minerals, glass, rocks, particle size, the abundance, are these components renewable? There's a whole host of issues that are simply not resolved and really critical for both science and exploration. Okay, last and by no means least is the radar measurements. These are, we really expected radar to be one of our premier experiments to identify ice on the moon because it's known from both Mars and icy bodies that you do have a distinction in the circular polarization ratio. So we thought it'd be, this is a piece of cake to detect it on the moon. Well, it's been challenging. There is a paper that Paul Spudis and his team worked very hard on, and this is again now the north pole of the moon. And the difficulty is that fresh craters give you blocky signatures, and it's difficult to separate that from when you might have signature from ice. And they came up with an algorithm, or at least a model, of looking for craters that have blocky on the inside and the outside being blocky, but if you have a high CPR signature only on the inside, that suggests those areas might have some form of ice. Okay, so where are we? Here's our various techniques. It's clear that the neutron spectrometer absolutely detects and maps hydrogen. No one doubts that. The imaging, we found no detection really. And sort of a similar, the laser altimeter, which uses similar approaches, at best ambiguous. The near-infrared spectrometer certainly detects and maps OH and H2O. There is no question of that. L-cross certainly detected multiple volatiles, but at only one point. And of course, the radar is a bit ambiguous, and the lamp is gives us hints of hydration, but it's very signal dependent. So we've got some winners, some hints, some ambiguous areas, and sort of the bottom line here is that there's a lot of outstanding issues that still need to be addressed from orbit. We really want to know what the distribution and abundance of water is across the surface of the moon, both the polar deposits, the superficial deposits, and the internal materials, the materials that Larry has been talking about. We want to know how the polar environment constrains the sequestration of volatiles. We want to know what the origin of superficial water is and how it cycles with time. And we want to know if there's any significant exposures of internally derived water or OH. So here's my last slide. What's the summary of all this? We know a lot more than we did a decade ago, but there's much more that really needs to be done from orbit to assess the nature of volatiles. And that's it. Thanks.
All right, thanks, Carly. There's a question typed in from Leslie Gert, which is, which regolith properties create the most difficulty in detecting water ice separately from mineral-bound OH or H2O?
So, say that again. Which? Okay.
Which
regolith properties create to detect separately? It's really to really distinguish OH and H2O spectroscopically, we need a little bit broader range of the 3-micron measurement. We at least need to go out to about 3.5 microns to get the character. We also need high signal-to-noise over that part in order to detect it. So we've got, M-Cube has given us the initial cut at that, but it has issues that we are still working with, and it's obviously on my high list of things that need to be done to get additional data from orbit.
So that feeds into the question that Mike Wargo typed in, which is, what would your priorities be for additional or ongoing remote sensing from orbit?
Oh, okay. I guess I answered that one. M4, but clearly in coordination with several of the other approaches. And that's, I think, something that we might want to discuss at the end of this discussion. That what kind of complement of instruments really would get us to the next stage of understanding of the character and distribution of water on the surface of the moon.
All right, and one from Murti Sirpada, which is, what is the origin of the Compton Belkovitch OH-H2O signatures?
Is Noah online? It's not up for me to answer that. However, for those of you who are familiar with Compton Belkovitch, it's a thorium anomaly. It certainly appears to perhaps be volcanic in origin. It has ample evidence that moderately recent activity, well, no, I shouldn't say that. It's a highly unusual area on the moon. Brad Jolliffe wrote a paper that integrated a lot of the LRO results of this about a year ago, and that sets the stage. And the water that we're seeing at Compton Belkovitch, or I loosely say that, OH, really is one more item that really characterizes this highly unusual area.
Okay, thank you very much, and we need to move on.